Hello and welcome to lecture 14 of chapter 3. We are still continuing our discussion of the electrostatic energy, but now precisely in terms of the electric field. Why? Because remember, first in the previous lecture we have defined the energy for the discrete system of charges as half summation of I qi vi, where Q was any of the discrete charges, Vi was the potential at the point where Qi sits due to all other charges, okay? And this was for the discrete system. And for the continuous system, we extended this to an integral, and that was W equals to half the triple integral, if it is a volume, of rho v, dq times v, the potential v, times the charge, which is rho v dq. Yes, okay? So these were the two expressions of obtaining energy of an electrostatic system, and both are obtained, as you can see, in terms of potential. Now we want to find the same electrostatic energy but in terms of electric fields. How can we do that? Let's start from this expression, but we know that the general form of the local form of Gauss's law in dielectrics says that divergence of D equals to rho v, and we mean by this rho v free. So we can put here, instead of rho v, div d. So the energy will be half the triple integral of rho v, which is div d, times the electric potential v times dq. Okay? But from our information of integral of calculus, of vector calculus, we know that the divergence, this is from now vector calculus, we know that the divergence of a vector, which is a scalar v multiplied by a vector d, is equal to v times the divergence of D only plus D dot grad of the scalar function V. V is a scalar function, D is a vector. V times D is a vector. The divergence of this vector is the scalar part times the divergence of D. Those are two scalars actually. Plus D dot the grad of V, which is a vector. Now, if you look at this expression here, it is div d times v. So it's this one. Therefore, W could be written as what? Half the triple integral of divergence of d times v is what? It is divergence of v times d minus d dot grad v. Grad v. All this times what? Times dq on the outside. Okay, so this is actually half into. Those are two integrals. The first one is the triple integral of divergence vd dv minus the triple integral of d dot grad v dq here. Okay, so that's dq. Okay, now if you look at this, that's a triple integral of the divergence of a vector times dq. Now this could be where did I obtain this dq from? This is dv right from the beginning, sorry. So that is dv, because rho v times dv, it is dq. Okay, v, sorry about that, v here, v there. Fine? Okay, and here as well. So from this, what do we have? If you look at this first integral, this is the triple integral of the divergence of a vector over a given volume. By Stokes' theorem, we can do it over, transfer it from a triple integral to a double one over a closed surface S of what? Of VD, the vector itself, okay, whose divergence is put here, dot ds. The second one is minus the triple integral of what? Of d times grad v, but we know that E is equal to grad v, is minus grad v. That's the relation between the electric field and the electric potential. So minus grad v could be substituted by E, so that will be d dot E times dv. Okay? Now this, we can extend this over the whole space. Over the whole space. Right? If you have a small volume, it will be bounded by a small closed area. When the volume becomes larger and larger, the surface area will become large and the radius will grow. If we include our integral over the whole space, then R will go to infinity. We know here that V is inversely proportional to 1 over R. D is inversely proportional to 1 over R squared, like the electric field. S is directly proportional to R squared. So the product will be R squared over R squared times 1 over R. This whole lot is inversely proportional to R. So when we go to infinity, that integral will be 0. And then we are left with what? With W equals to, here this will be a plus sign because minus grad V is E. So it will be the triple integral of D dot E dV. Definitely there is a half outside here which was there. So this is half. So W, we can write this as the triple integral. D is epsilon E dot E. But you know that E dot E is E squared, so we can finally write this as W equals to what? The triple integral of half epsilon E squared dV. This is over the whole space. Over the whole space. So if you want to find the energy due to any continuous distribution of charge, you can do it this way in terms of potential or that way in terms of field. As you can see here, we are integrating something dV over the whole volume to find the total energy. So that thing which the integrand here is what? That is the electrostatic energy density per unit what? Per unit volume. It is very similar to mass per unit volume, mass density, charge per unit volume, charge density. This is energy per unit volume. It's called the energy density. Okay? So whenever you have any distribution of continuous charge and you have the field, you know the field due to this distribution, at points inside distribution and at points outside as well, you have to integrate this over the whole space, inside and outside the charges, in order to find the total energy. While here, the integral is only carried out over points where the charges exist, because you have a rho v. Here you have an E. You can have an E field outside a charged sphere or ring or whatever, while here you cannot have an energy due to V at points outside the distribution. Okay? So these are two alternatives as how to find the electrostatic energy, either in terms of potential or in terms of field. Okay? Let me take one or two applications. Let's start with an easy application of the energy stored in a parallel plate capacitor, for example. Okay. Let me do first the energy stored in a capacitor in general, and then we'll do it for a parallel plate capacitor with more than one method. Okay, that's example 318. Okay, if you have a parallel plate capacitor or any capacitor, you know that capacitors in electric circuits are given this symbol, whether they are parallel plate or not. So this is a capacitor in general. Let's try to find the energy, the expression of energy in general of this capacitor. During the charging process, you are collecting charge. If the charge collected during the charging process is Q at one plate and 1 minus Q on the other, then starting from this situation, if you want to add a dq here and a minus dq there, then you need an element of energy, which is what? Which is the potential difference at this point, V, times the charge dq. But the amount of the potential difference between the two plates when the charge is equal to Q is how much? We know that V is equal to Q, the charge Q, over C. This is times dQ. So that's the element of energy. So the total energy which is needed to charge the capacitor fully until the total charge on the plates is Q here and minus Q there is the integral of this from 0 to Q of Q over C dQ. That is 1 over C. C is constant as long as the geometry is known and the medium, the dielectric medium between the plates is fixed. Integral of Q dQ is Q square over 2 between 0 and big Q. So that is Q square over 2. So that's half Q square over C. This is the energy expressed in terms of the final charge and the capacitance. You can also write Q equals C times V, where V is the final potential difference when the capacitor is completely charged. And then you can put this in here to obtain either half, that's C square V square, so C V square, or half, instead of C you can write Q over C, that will be Q V, or the third one, so this is one form, a second one, a third one. This is the expression of energy, as you can see, in three ways, in terms of Q and C, in terms of C and V, and in terms of Q and V. Okay? Now you can apply this to any capacitor of any geometry. For example, now for the parallel plate, capacitor, the energy will be what? Half Q squared over C will be what? Epsilon A over D. So that is the energy stored in a parallel plate capacitor when it is completely charged with a charge big Q. Okay? Now, you can later do what? Try to obtain the same amount of energy by applying the last formula which we derived in terms of the electric field E. And we can do that and compare this to the result we obtained now. Okay? Fine. So now, let me remind you that W was half the triple integral of, let me put the half inside, half epsilon E square dV. What is the value of the electric field between the plates? We know that the electric field between the plates of a parallel plate capacitor is sigma sigma s over epsilon 0. Okay? Because it's the field due to this and that. This means that W will be what? Triple integral of half epsilon rho s square over epsilon 0 square and epsilon 0 here times dv. All these are constants, so this is equal to half rho s square over epsilon 0 triple integral of dv. Luckily here the field between the plates is uniform, so we took e square to the outside. Triple integral, it will be the total volume, triple integral of dv. So that is the total volume, which is which is the separation d times the common area A. But we know that rho s is what? This is half and epsilon 0 here. Each rho s is q over A, because we assume that the total charge is uniformly distributed over the area. So that is q square over what? Over A square times A times D. So that is half and epsilon 0 here. That will be a q squared times D over A. If you compare this one to that one, you will obtain the same thing. You can also, if you want, try to do it with a third method, using the expression of W in terms of V, not in terms of V. How do we do that? I'll keep these two answers. This is a third method. I'm doing all these methods just to let you see how important or how nice is to know how to solve a problem in electromagnetism or in general in any branch of science with more than one method and obtain the same answer. If you want to apply the third relation, which says half triple integral rho v times dv. Now in this case, we want to find W at points where charges exist. In a parallel plate capacitor, there are no charges between the plates, there are charges only on the plates. So you have two plates here, this one positively charged, that one negatively charged, and then W will be what? You have to do not a triple integral because you don't have a rho v, you have rho s here and rho s there, okay? Here the potential, if you take this and as an origin of potential, for example, 0, the potential here will be V, because this is a positive charge at higher potential, okay? So in that case, when you do the expression will be double integral now of rho s times V ds. If you do it here where the potential is 0, you'll obtain 0. If you do it here when the potential is V, that will be half double integral of rho s and V. Rho s is constant and V at all points of a conductor is the same because the surface of a conductor is an equipotential surface. So that will be a rho s times V times double integral of ds is A. So this is half rho s times. Now V, what is V in terms of E? It is the field E times the separation D. That's V times A. This is equal half rho s times the field E again is rho s over epsilon 0 times D times A, and that will be half and epsilon 0 here. We can write up there A squared and A down here to obtain A in the numerator, multiplied here by rho s squared. What else do we have? We have a D here. So that is half and epsilon 0, A squared, rho squared. Each rho s times A is the charge Q. So this is Q squared times D over A. Look at this beautiful answer. That one and that one. You have to have the patience always to do these things and obtain the same answer. The same answer of the energy was obtained how? By applying or using 3 different approaches. Okay? Now, what else? Definitely you can think of many applications. Let me remind you of example 317, which is this one, the one before this exercise. Example 317. Remember that following each example, there are 1 or more exercises where the given is done. You have the given and you have the final answer. Try to obtain these answers. So 317, we had, if you remember, a sphere, charged sphere of radius b, okay, and of either we know the volume charge density rho v, or we know the total charge. And our task is to do what? Is to find the total energy stored, electrostatic energy stored in this sphere, dielectric sphere of radius b and volume charge density rho v, or you are given Q either 4/3 pi b cube times rho v. That's the total charge. Okay? How to find the energy of this sphere? Again, if you have the patience and you have the muscle, you can obtain the answer for this example in 3 different ways. Number 1, you can do it using W equal half the triple integral, as we have seen before, rho v times big V dV. Repeat, rho v is any point, the charge, volume charge density at any point. V is the potential at any point inside after collecting the whole charge, and dV is an element of volume. You can do it this way, or you can do it using what? The electrostatic energy in terms of field. That's half triple integral. That triple integral is only on places where the charge exists, while this second triple integral is over the whole space where the electric field exists, unless there is a region of space with no field on it. That will be, I would like to put the half inside because it is a part of the energy density, half epsilon E square dV. Okay? That you can collect the charge either in vacuum, where you have epsilon 0, let's assume this simple case, or you can collect it and put it in a dielectric where the permittivity is epsilon, not epsilon 0. This is one method. That's another method. A third method, which is given in your book, is by splitting this sphere into small concentric spherical shells. You find the energy to build each shell after building all the sphere below it, and then add all the energies of all shells. Okay? Next time I'll try to give you an idea about how to proceed with each of these approaches and how to obtain the same answer. Okay? For now, I will say goodbye to you all and see you next time.